All right, welcome everybody. So this wasn't really a video I was planning on doing, but I just figured maybe this might help, and might some of you that are working on characteristics of functions. This is for my pre-calculus class, and this is actually the PowerPoint that I did today in school. And what I did is there was obviously some corrections that I wanted to make to the PowerPoint, so I'm working on that and making some corrections that I'll update obviously for future use. And then I just noticed, I'm like, why don't I just record what I'm going through, kind of what I talked with my students, kind of do a quick little version, because I am making another video that is very similar to this one, that is going to be a little bit more in depth. I'm going to be a little bit more doing the teaching. But for this one, maybe some students just want kind of like a quick little refresher, and then to see my examples and see me kind of talk my way through it. I'm like, why don't I just do that? And then that might help some other students that maybe don't need me to instruct as much for them. Because I obviously already spent all day instructing off of this PowerPoint. I don't want to do another lesson on that, but I will be having another video coming up that's going to kind of do just that. So this is the characteristics of functions. And again, I'm just going to kind of work through the PowerPoint slide, not really as I was teaching, but just kind of to refresh and kind of give you guys an idea, basically what my students were learning today as far as learning the individual characteristics of a function, what makes up a function, and kind of how functions are unique. So what we did is we started with a warm-up, and I asked them just to kind of describe this graph and, kind of think of like as a kid, how they would do that. And then we kind of talked about, just some basic things, not really getting around math, things were broken, when does it go up, go down, maximum, minimum, symmetry, and all that kind of fun stuff. And then I kind of showed them these graphs, that these are the graphs that we work on, that these are the ones also that I'm going to help describe to you as far as their characteristics. And so therefore you can kind of see all these graphs here. And then the last thing I said is, what do these all have in common? And obviously I just kind of wrote this in there because I stopped in before and I was like, they're all functions. But I'm sorry, I was fixing my notes here. So we talked about, yeah, they're all functions. All those functions, they look really, really different, right? None of them look the same, but they all are functions. And so that kind of progresses into our definition of a function, what basically makes up a function. And I thought I had that in there. But one thing I talk about with the function is the input, or in the input independent. So the input, I put that in domain range, and output. So this isn't as obvious when we get into the, we're just looking at a graph. You're not really thinking of input and output, but that's just a very important understanding and basics for understanding a function. So then we talked about the kind of looking at examples, and for this kind of lesson, we're only going to focus on the graphical approach, and the main thing talking about the vertical line test. We did kind of previously talk about, in previous, courses, you might have talked about a table or mapping to look at a function. And then also, if you talk about a function in terms of equations, it's only a function if you can solve for y explicitly. That means y by itself, not going to have two or more answers. So this is not a function, which I didn't write in there. So this is an example of not a function, and this is a function. All right, so then we kind of went into function notation and, kind of explaining to students what function notation looks like so they can kind of, get used to it in case they kind of forgot and it's something that's always confused them. And then we kind of moved on to the stuff that we're going to be talking about. So here's the domain and range I went over. So, domain and range, very important. But when we're looking at the graph, sometimes we think about domain and range differently than when we're thinking about a table or an equation. And so the main thing that I wanted to talk with students, as far as the domain and range is, basically the set of x values that make up the graph. And actually, I'm going to write that up. So for a graph, so when we're thinking about a graph, it's the set of x values, there's an E there, that make up the graph. And that could also even be further simplified as to how far left to how far right. Now, that's an oversimplified vacation of the domain because that doesn't always work, as we are going to see. but it's, you know, it's at least kind of a helpful tint for at least to get started, because that is for the domain. And when we're talking about the range, again, I'm just kind of writing this in here because I'm going to think about when I'm changing my slides and adding things in. These are some things I'm going to write in there. So you guys are just kind of really watching me kind of go through my lesson plan and fix things up. So it's a little bit different video than me, you know, obviously making something in class. A lot of times you guys just see my videos, you know, not really polished, but just see my videos in class. Well, this is just kind of one me behind the scenes, you know, working on my lesson. So this would be the set of y values that make up the graph, and that's also like the output values, and that's basically can also be further simplified to how far down to how far up. Okay, way simplified though, because we have these things called asymptotes and discontinuities, which we're going to come up to. But anyways, hopefully that at least starts. So we looked at the table and points in my previous class, so that's kind of was like a little review. This is obviously what we're going to be dealing with in this chapter, and then I left the equations for next class, so I'm going to take that out. The main important thing I wanted to kind of get with students is, you know, we might have talked about domain in a lot of different variations. Well, in our class, we're going to only really kind of focus on interval notation. And interval notation is basically kind of like start to end, you know, left to right, down to up. So really kind of think about that start to end is really kind of a simplified way to understand that. And so if we want to write all real numbers for the domain, which is the domain of this graph, all real numbers, then we just write, you know, parentheses, negative infinity to other parentheses. And the reason why, again, we're using parentheses is because the infinity is not a number, so it's not defined in the function. And then when we look at the range, you can see that is that goes as low as 0 all the way up to infinity, but 0 is a y value on that graph, so therefore it is included. So for included values, we're going to use the bracket, and for the non-included values, we're going to use parentheses. All right, then we got into continuity, which is pretty basic. It's either something is, you know, continuous, or it's going to have holes, jumps, and asymptotes. And what I just said is what we call our discontinuities. So just kind of a very generic, you know, kind of way for us to look at when the graph is not continuous, these are some ways that it can be broken up. So, you know, just kind of looking at this, a hole can be just an open circle, and it can be defined at another point in the graph, or it can just be an open circle in the graph. Obviously, a jump, you can see that's like a break from one part of the function to another. And then we have the asymptote, basically a line where a graph is going to be approaching, but it's not actually a, you know, line on the graph. And remember, vertical asymptotes cannot be crossed either, or not actually met. Then as far as the extrema, I kind of wanted to rewrite these definitions. How I did this, you know, basically when we're looking at the absolute maximum and minimum, those are basically going to be the highest and the lowest points of a graph, the absolute highest point or the absolute lowest point. So you can have more than one. Like basically, if you both have 2 points that have a height of 7, then they're both absolute maximums. The main important thing, though, that I want to use for my definition is every point to the left and to the right of the maximum point has to be below. Therefore, if your absolute maximum point occurs at like an endpoint, which I show, then I'm not going to consider it an absolute maximum point. And that goes the same for a relative maximum. Every point to the left and to the right has to be below it. And obviously minimums would be above. So just kind of looking at those examples, you can see I don't want the absolute minimum to be at the endpoint. It's going to kind of change the graph. I'm going to use this graph now instead, so you can see that there's multiple of them. Relative is kind of the same thing like local. It's not the absolute maximum. It's just a maximum point or a minimum point. As you can see, this graph continues down. Then we looked at boundness, which is basically like the height restrictions. If a graph can only go as high or as low, we can say it's going to be bounded. Increasing, decreasing intervals. The main thing here is when versus how. A lot of students always want to talk about how high the graph goes up or how far it goes down. You know, for instance, here, the graph is going up. Remember, you're reading the graph, and that's actually something I'll add into there. So just make sure you read the graph, because a lot of students have trouble with this. They were thinking left to right. A lot of students were thinking that the graph was, rising because they're reading it from right to left. So as we're reading it from left to right, you can see that this graph is going up, right? As I'm coming across here, as I'm doing the x values going over here, you can see the graph is going up. So it's going up from -infinity to -1. That's when the graph is going up. How high the graph is going up, you could say from -infinity to 5. But when we're talking about increasing, decreasing intervals, we're talking about the when, not the how. And then we went into even and odd functions. That's going to basically be about the symmetry. Even functions are symmetrical about the y-axis. Odd functions are symmetrical about the origin. And basically just flip them over the axes. If there's no symmetry, then it's neither. And then we talked about end behavior. I kind of got a little overexcited with this when I was first creating this, so I started working into some math notations. But for this year, I just wanted to kind of keep things simple, so I'm going to simplify this here. The main important thing is, looking as this graph is expanding, where is it going? And that's basically what end behavior is asking us. And notice though, if the graph stops, then there's no end behavior. If it approaches a horizontal asymptote, then the line of that horizontal asymptote is going to be the approaching value. In this case, it's 3. And then there's one other example I did not cover, which would be the oscillation approach. So if you have a graph that's oscillating, then there's no end behavior. All right, so, and then last but not least, x-intercepts. I need to redo these examples. They were kind of hard to see. But the main important thing I want to talk about here is, when you have discontinuities such as a hole or an asymptote, those actually aren't discontinuity, or those actually aren't intercepts, so don't put them in there. All right, so then what we did is we went through the graphs, and we basically went ahead and labeled each and every one of them. So that's what I kind of want to do with you guys, is just kind of go through these and talk my way through all of these examples. So I think I have 5 of them. So if this is something that's helpful, I'm just going to kind of go through everything that I just explained one more time. So in this example, my domain, you can see that this graph is continuous. So my domain is going to be all real numbers. That kind of looks like it's a negative, which is not supposed to be. My range, in this case, you can see basically that since it's continuous again, my graph goes all the way down to 0 and all the way up to infinity. So since it's continuous, I'm going to use 0 to infinity. Let's see, the inner values that the graph is increasing. So we can see from -infinity to 0, we can see as I'm moving from left to right, you can see the graph is going down. So I'm going to say for my decreasing values, let's do that first. That's going to be -infinity to 0. And there's another one, so I'm just going to use a union symbol to connect them. A union is just bringing them together. It's also going down from 1 to 2. And again, that's the x value, 1 to 2. And then we can see that it is increasing. And we can see that's increasing from the point 0 to 1. And then from, not 1, 2 to infinity. All right, discontinuities. There is no discontinuities. It is a continuous function. So I'm just going to write none. The extrema, well, we have a couple things going on here. We see that we have a lowest point, so that is going to be our absolute minimum. I'm just going to use ABS to represent absolute. So our absolute minimum is going to be at 0, 0. Yeah. All right, then we have some other points that looks like highs and lows, right? So this again is another minimum point. The points to the left and to the right are above it, so therefore it is a minimum, but it's not the absolute. So therefore it's going to be a relative minimum. And actually, I forgot to write in there. So an absolute min, that looks like ABS min. So absolute min is going to be at 0, 0. Jeez, man, it's been a while since I've been using this pen, I guess. And then we'll have a relative min at, let's see, that's at 1, 2. And then looks like we have a maximum. It's not the absolute maximum because the graph continues going up. So therefore, we're just going to call that a relative max. And that is at 1, 3. Cool. The graph even, odd, or neither. Again, we're looking for symmetry. This doesn't have any symmetry, so we're just going to write neither. Boundness, this graph is restricted below, so it only goes to a minimum thing, so we can say this is bounded below. All right, the end behavior, as this graph goes and expands, you guys can see that it's going to rise to the left and rise to the right. All right, and the x and y intercepts here, you can see that the graph crosses the x and the y intercept at the same point. So we can just say that x and y intercept is at the origin, 0, 0. All right, and there we go, guys. Basically what we're going to do here for the next couple graphs. So 1 down, 4 more to go. All right, next one is, this one looks like a set of lines, you know, kind of be like a piecewise function. However, we can see that the graph is defined for all x values. So I'm just going to write the domain is going to be all real numbers. Let's see, the range here. Looks like this graph is going all the way down to -infinity. And then it's going highest to. Now there's multiple points that represent the maximum, or a maximum value here, but that is a value that is thing, so I'm still going to use a bracket here. There's just not an absolute maximum, which I guess we'll get to in a second. The next one, increasing. Well, we can see from -infinity to, let's see, what is this, -3. The graph is increasing, so I'll just write increasing from -infinity to -3. And again, one thing I forgot to mention when we're dealing with increasing, decreasing, and constant intervals, that we're only going to use parentheses. We're not going to have included values, because you can't have, you know, -3 can't be increasing and constant at the same time. Let's see, we're going to use a constant interval. Is going to be from -3 all the way to 1. And a decreasing interval is going to be from 1 to infinity. See, if I used like, well, actually that one would be fine, but here, this -3 can't be increasing and constant at the same time. Discontinuities, looks like we do have a jump discontinuity. And then the location of that is when x is equal to 1. The extrema, there actually is no extrema in this case, at least for the definition of for any point here that to the left and to the right has to be below. You know, you could get into there's infinite many absolute maximums because these are all highest points, but per our definition that we're going to use, you have to have points to the left and to the right that have to be below it. So therefore, this has no extrema. And then we want to look at even, odd, or neither for looking for symmetry, and this would be an example of neither. Boundness, though, so it doesn't have an absolute min or absolute maximum, but we do see it has an absolute maximum value, which is 2. So therefore, it is bounded above. All right, and then we have end behavior. You guys can see that this graph is going to fall left and fall right. So just say falls left and falls right. Okay, and the x and y intercepts here, we can see that looks like the x-intercept, there's 2 x-intercepts. So the x-intercept is going to be at -4, 0, and also at 2, 0. Whereas the y-intercept is going to be at 0, 2. So just make sure when you're writing in the intercepts, you know where, what is the x-coordinate, x, y, which one's 0 for each intercept. All right, next one. Looks like a lot of lines and going on through here. So the domain and range here. Now, when we're doing the domain and range of something that's been broken up, obviously what we're going to want to do here is just basically do the domain of each section separately. And that was one thing actually I forgot to mention over here. The domain here, even though this has a discontinuity, the function is defined for all x values, right? At 1, the function is not defined up here, but it's defined down there. And as this graph expands, it's always going to be defined for every value. Now, down in this example here, we have some asymptotes, and we know the function is not going to be defined. So let's just kind of write in on the graph where the function is defined. Well, actually, let's just write it here. So the domain. So our domain, first, as far left as it goes, is going to be -infinity. And then it's going to keep on traveling to the right until it gets all the way to -2, where it starts to be undefined, right? So it's not going to be defined at -2. So I'm going to use a parenthesis. Then, after the parenthesis, it is defined again. So from -2 all the way to 2, the function is again defined. So I'm going to just add another domain here from another interval from -2 to 2 the function is defined. Then at 2, it's undefined. There's an asymptote. But as I hop over that asymptote, you can see again, I am now defined again all the way to infinity. So then we go from 2 to infinity. And then mathematically, I'm going to connect these domains just by using the union symbol. As far as my range, I guess I'll do that above. The range is again asking, how low is this graph going to go? So that looks like it's going all the way to negative infinity. And then it only goes as high as negative 1. Now, negative 1 again is a defined value, so I'm going to keep that there. Now, nothing happens in this space until after we get to this horizontal asymptote, which is 1, and then after that up, we go ahead and get the function is then defined all the way up to infinity. So that's going to be union 1 to infinity. All right, so increasing intervals. Man, there's a lot going on here. So let's do B down here. So the graph is increasing. So we can see as we're reading this graph from left to right, the graph is increasing from negative infinity to negative 2. The graph is increasing here from negative 2 to 0. So I'll just do 0, negative 2 to 0. And then we can say the graph is decreasing from, oops, did I write? Yeah, 0. The decreasing from 0 to 2, union from 2 to infinity. And again, when we're looking for something to be decreasing, we're looking at the y values. Are the y values going up or the y values going down? But we're describing it based on the x interval. Discontinuities, we have 2 asymptotes. So we have so we can say an asymptote at x equals negative 2 and x equals positive 2. Now, you might look at this and say, well, what about this horizontal asymptote? Well, horizontal asymptote was not in our description of our discontinuity, so therefore it's not going to be considered a discontinuity in this discussion. So only vertical asymptotes are going to be considered discontinuities as far as breaking up the graph. Then we have our extrema, and you can see that this point here looks like it is a maximum. Points to the left and to the right are going to be below it, but it's not an absolute maximum because as this graph expands, you can see that it keeps on going up. So we have a relative max, also known as a local max, and that relative max is going to occur at 0, negative 1. For even, odd, or neither, we see symmetry. Looks like this is symmetrical about the y-axis. So I'm just going to write it is even. But we can see as this graph expands, it's going up and down. There's no restrictions on how high it is. Even though we have this restriction here, the graph continues going up. So therefore, it is unbounded. Then we look at end behavior. It's like, where is this graph going? As the graph expands, looking to the left and looking to the right, where is the graph going to go? And one thing we're going to talk more about is looking at these horizontal asymptotes and seeing how that affects the graph. But that's going to be actually our end behavior. You can see as this graph goes to left and right, you can see that the graph is approaching y is equal to 1. So we can say from the left and right, I'll just say approaching y is equal to 1. And then x and y intercepts, we can see that the only thing that's going on here is a y-intercept. The graph does not cross the x-axis at all. So we have a y-intercept, and that's going to be at 0, negative 1. Okay, now on to the next one. So the next one is kind of interesting here. Notice that we have this dot here. And so we have a hole, which has a defined value point, and then we have another hole where there's not defined point. So it's kind of interesting here. And the graph obviously does not expand. It just is, contained. So our domain. All right, so let's look at the domain here. So the domain is, basically how far left, how far right. Well, the function is defined here at negative 4. Even though it's not defined there, it is defined at negative 4. So I'm going to start with negative 4. And then I'm going to keep on going to the right. And you can see, oh, it's not defined at when x is equal to 0. And that's it, right? It's not defined at 0, so I'm just going to stop. All right, and then it looks like after 0, it is defined all the way to positive 4. So I'm going to do union 0 to positive 4. And again, I'm using the brackets for values that are defined. Negative 4 and 4 are defined on the function. 0 is not. When we're looking at range, we're looking at basically how low the graph goes to how high. We can see the lowest point is 0, which is defined. It's not defined there, but it's defined there. And then it's going to go all the way up to 4, which is a open circle. So therefore, that is going to be undefined. All right, increasing, decreasing intervals. We can see that the graph is increasing from negative 4, right? From down here, even though here's the point, right? That's at negative 4, right? And that's why negative 4 is not included. But right after negative 4, all the way up to 0, the x value is increasing. So again, from negative 4 to 0. So as my little marker is going from left to right, the graph is going up. So negative 4 to 0. And then we can say that it is decreasing from 0 to 4. All right, discontinuities. We have two holes. So we can say there are holes at, and then we just want to give our location of the holes. X equals negative 4 and x equals 0. The extrema, again for extrema, we got to have points to the left and to the right that are going to be below it for maximums, and points to the left and to the right that are going to be above it for minimums. And here, this looks like a low point, but we don't have any points to the right, so therefore it's not going to be considered an extrema. Here is a point that looks like to the left and to the right or below it. The only problem is that's actually not a point. It's just an open circle. And here, again, we're dealing with that endpoint example. So the extrema, in this case, is going to be none. As far as symmetry, it looks like it's symmetrical about the y-axis, especially if this was a dot over there, it would be. And if that was filled in, it would be, right? It'd be perfectly symmetrical. But it's not, unfortunately. There's no symmetry here. So we're just going to say even, odd, or neither. So this is neither. The next thing is boundness. You can see that this graph is restricted on its height. It can only go so low and only go so high. So therefore, this graph is what we call bounded. And behavior, obviously, as this graph expands, it doesn't really expand, doesn't really do anything, right? It's going to stay there. So therefore, this graph has no end behavior. And x and y intercept. So again, remember these are holes, right? Those are not actually points on the graph. So the only thing we have is one x-intercept, which is going to occur at 4, 0. All right, now let's go ahead and get into the last one that we covered here in class. Actually, not the, well, I'm going to do one more. One more that we have that I forgot to move around the slides. So the next one is the domain and range. For this one. So this one looks a little bit different than the one I gave my students. And this is actually a repeating graph. And I didn't tell my students that because I just wanted to keep things simple. I knew this was going to confuse a lot of them. And it's something that we're going to get to later on in the year. But I just wanted to kind of just get their mental juices kind of flowing. So in this case, we have the domain. Now, what you can see is we have a lot of asymptotes, and the graph and the asymptotes are just going to keep on repeating. So that kind of brings up a problem because in each of these sections, let's see, for this one is -1 to 1. And then this domain is going to be from 1 to 2. So one thing that we kind of notice here is, the domain, basically has the domain as a distance here of 2, right? Like each one of these asymptotes is occurring every 2 values. So what we're going to look into doing is just different ways we can write the domain. So what I can kind of say here is I can basically say like -1. Now, if I want to get from -1, the next asymptote is going to occur 2 more units over. So I'm going to write plus 2n, comma, the next asymptote is 1 plus 2n. Now you might say, well, what is n? Well, again, this is something we'll spend a lot more time on, but n really just represents a number. If n is 0, my domain is -1 to 1. If n is 1, then my domain is 1 and 2. If my n is -1, then therefore I would have my next domain, which is -3 and -1. So you can see how when n represents any number, that can give us this domain. And there's other ways we're going to write that domain, but this is one of the ways that just to kind of trick people around, get them excited about what we're going to be learning this year. That was kind of my joke. The next one is the range, basically how low the graph goes to how high. So therefore, that's going to be from negative infinity to infinity. This one's kind of interesting. As you read from left to right, the graph is always increasing. And again, the increasing intervals are repeating. So the increasing intervals is going to be the same as the range, as the domain. So it's increasing from -1 plus 2n, comma 1 plus 2n. Discontinuities, obviously we have asymptotes, and those asymptotes are repeating. So the best way to write this is just to pick an asymptote, and then obviously we know the distance between these asymptotes is going to be 2. So we're just going to use let's just use 1. So we'll have asymptote equals x equals 1 plus 2n. Extrema, there obviously is no max or min, so that's going to be none. Even, odd, or neither. This graph, if you take this graph and reflect it about the y-axis and then reflect it about the x-axis, you can see that it will be exactly the same. So this is actually an odd graph. The graph obviously continues going up and going down as you would expand it, so therefore it is unbounded. The end behavior, this graph repeats, right? Even though it looks like it's falling to the left and right to the right, it keeps on repeating. So unfortunately, when we're having something that is repeating, that's not actually going to be a good description of the end behavior. So therefore, this would have no end behavior. And then obviously we have our x-intercepts. So what we can do here, we don't have, or the x and y-intercepts actually, are both repeating. So x-intercept is, again, let's just pick the first one, 0. So that's going to be, let's write this as, so 0, and then the y-coordinate is 0. So that's going to be 0 plus 2n, comma 0. So in reality, that's just going to be 2n and 0. And then, so the y-intercept, I'll just write that as 2n, comma 0. So this was a difficult one, and again, really not something we're going to be teaching or going over and for a couple more months. But I thought it would be one just to kind of expose some students to, so therefore when we get to that point in the lesson, they are a little bit more familiar with it. But if you wanted one more example and not something that difficult, I will kind of go through the one. Oh, I forgot I need to go through that. I will go through at least the last discussion here that we did on this one, and this was the warm-up that I gave the students. Or this is at least my teacher direction. So let's go ahead and do this one real quick. So in this one example, the domain that's undefined, or that's defined, that's undefined. So therefore you can see this is all real numbers. We can see the range. The graph only goes down to -2 to infinity. The graph is, let's see, it's increasing from the x interval, sorry, to infinity. It is decreasing on the x interval, -infinity to -4, as well as on the x interval 0 to 2. So from 0 to 2, the graph is going down. And then this one's also constant from -4 to 0. Okay, the discontinuities, we have a jump at x equals 0. Extrema, you can see that we have an absolute minimum here at 2, -2. All right, and this absolute minimum occurs at 2, -2. But let's see here. But yeah, that's going to be it. We're not going to consider these as an absolute max or an absolute min. Even, odd, or neither. This function has no symmetry, so therefore we're just going to say that this is neither. The graph is bounded below, but it's not bounded above because there's no restriction. So we're just to say this is bounded below. And behavior, as this graph obviously expands, you guys can see that it's rising to the left and rising to the right. Rises left and rises right. And the x and y intercepts, obviously this is an open circle, guys, so this is not going to be a intercept. But here we have a y-intercept, and here we have an x-intercept. So we can say the y-intercept is going to be at 0, 3, and the x-intercept is going to be at 4.0. All right, and that was kind of it, guys. Hopefully, you have, here's kind of like my reflection questions, and hopefully you guys kind of like this lesson. I really was not planning on making this video. This is really something that I just do in my class, and I am using this to create a video that's going to be a little bit shorter that I will be coming out on to kind of give people that really need the instruction a little bit more in depth. As I was kind of talking, I forgot about some things. But, here's a little bit of reflection. If you want to reflect on those and post those in the comments, I would love to kind of hear, even through this, even through me doing this lesson again, if there was some things that you understood or maybe some things that you were still having some questions on. So feel free to add those into the comments below. And then also let me know if you guys like this, because I created a lot of the content, obviously in my classroom, and one of the things I'm doing is working on, putting them into the PowerPoints to kind of teach from this perspective this year. So I will be doing a lot of this work, exactly what I did here, and I can do it much quicker if I am not making a video. But if this is something that you enjoy and this is helping you out, then I am more than happy to kind of continue doing this. And just let me know in the comments below. And obviously, guys, we'll be making some more videos this year. Cheers.